So now let's see what these steady flow devices are that could be interesting to us. Well, here they are. There's 6, and I say there's 6, although if you count them, it seems like there's many more, but some of them are reverses of each other. For example, a nozzle is basically the reverse of a diffuser, and a turbine is essentially the reverse of a compressor. So the devices we have are nozzles and diffusers, we'll call that as one, compressors and turbines, mixing chambers, heat exchangers, throttling valves, that's the one in the lower left that looks like a pipe with a valve in it, and then finally duct flow devices, devices that have heat interactions and work interactions because you've got a fan pushing things through it. These are very common devices to which we can apply our steady flow equations of mass conservation and energy conservation. Now you might look at this and say, well, yeah, where am I going to use this in everyday life? I think this is stuff that's probably in industry somewhere, and I'll never have this. Well, actually, you probably already have every single one of these. If you took a shower and you mixed hot and cold water, you have a mixing chamber. It may be behind the wall, you may not see it, but you have a mixing chamber. The two streams that come in are cold water and hot water. Okay? You mix them out to a comfortable temperature so you can take a shower. You might look at that and say, okay, but what about a heat exchanger? I mean, I've never seen a heat exchanger in my house. Well, that's because it's hidden behind some ductwork. If you have central heating or central cooling, central air in your home, or even in your car, if you have an air conditioner, or even if you have heat in your car, which is, as far as I know, ubiquitous, it's everywhere. Or every car that you buy today has a heat setting, so for the wintertime you don't freeze. Then you have a heat exchanger and you use it. And what does that heat exchanger have flowing through it? Well, if it's an air conditioner, then you have refrigerant flowing on one side and air flowing on the other. So you're trying to cool down the air. And you can't destroy the energy that air has. It has to be sucked out and put into the refrigerant to be put somewhere else, to basically be pumped outside. So technically an air conditioner is more of a heat pump. Now, in the typical vernacular of HVAC, you wouldn't call an air conditioner a heat pump, but that's what it does, really, is it pumps thermal energy out. A lot of people are really confused about things like air conditioners and refrigerators. They think that freezers and refrigerators generate cold air. Nothing could be further from the truth. You can't make air cold. The only thing you can do is pull thermal energy out of the air, and that thermal energy has to go somewhere. You can't just destroy it and poof, it's gone. It doesn't work that way. Nature says no, okay? So energy has to be conserved. So if you ever get the chance, stand in front of the refrigerator in your home. What you'll probably notice is that the floor near the refrigerator is warmer than the surrounding floor. And you can feel it, especially if you take your shoes and your socks off and your feet are just bare on the floor, because most of the times in a kitchen you've got some solid floor. It's usually not carpet. Carpet's kind of a really bad idea in a kitchen, right? But if you stand in front of your refrigerator, most of the time you will feel that the floor in that area is warmer, and that warmth, that thermal energy, is actually coming from inside of the refrigerator. It's being pumped out and basically being raised to a higher temperature so that it will flow into the kitchen environment instead. So if you have, you know, a refrigerator in your home, you have a heat exchanger. As a matter of fact, let's count how many we've encountered. There's the heater core in your car for keeping you warm in the winter. That's one heat exchanger. There's actually two heat exchangers in your car for air conditioning. There's a coil in the dashboard somewhere and one in the engine compartment. And there's the radiator in your car. So that's 4 heat exchangers just in your car. In your house, if you have central air, or even if you have a window unit, you have at least 2 heat exchangers. There's one inside of the home and one outside of the home. And then you've got a heat exchanger in your refrigerator or your freezer. Okay, so there's at least 3 most likely in your home, unless you simply don't have air conditioning in your house. Now my guess is that you also have heat in your house, central heating, okay? Unless maybe you heat your house with a wood stove. In that case, you have a 4th heat exchanger in your house. Even if you heat your house with gas, the hot exhaust gases have to go through tubes, and air from the home have to be blown across the outside of those tubes. So that's a 4th heat exchanger in your house. You have 8 heat exchangers you deal with on a regular basis just between your home and your car. So you certainly use these devices. What about compressors and turbines? Well, that one's a little harder. You may or may not have a turbine or a compressor, but if you have a air compressor in your home, or let's say you have a little air compressor for roadside emergencies, something that runs off the cigarette lighter, that is a compressor. Now, it may not be a steam compressor like this or a turbine compressor. It may be a piston compressor, but it's still a compressor. There's also a compressor in your air conditioning unit. The refrigerant has to be compressed. It's in a gaseous form, so it's not a pump. It's a compressor because it's squeezing down and pressurizing gas. So you probably actually do have some type of compression device. Now, a turbine, that's a little more difficult to find, but usually dentists actually use turbines. If you ever have your teeth worked on and they use a drill, a dentist drill, then that whirring, whining noise you hear is actually a little turbine inside of that little almost pencil-sized device, that drill, that turns the end tool for cutting into your teeth and hopefully patching them up so you can use them a little longer. So that's one place where you may have experienced it. What about nozzles and diffusers? Well, here I'll have a big problem, but if you've ever flown, then the jet engines use nozzles and diffusers. You may have seen nozzles on the back end of jets, for example, fighter jets, for example. That was, I admit, a little bit harder to say you've got one in your home somewhere. But the throttling valve, that little pipe with a valve in it, again, if you have an air conditioning system in either your car or your home, you definitely have a throttling valve. I have what would be termed a heat pump in my home, so it can both heat my home in the wintertime and cool it in the summertime. And in this case, I actually have two throttling valves. You have to have two separate ones for expanding the gas at two different places, one inside the home and one outside, for the sake of efficiency. But even in your car, if you have air conditioning, you certainly have a throttling valve. The last example for duct flow, well, again, if you have ductwork in your home for central heating or air, you certainly have a fan in the ductwork. And if you use a hairdryer, for example, you have this as well. This is essentially a hairdryer, right? You've got a fan that pushes air through, and you've got a heating coil that heats up that air so you can dry your hair in the morning. So these are all very useful and interesting devices. You may say, okay, I get that they're useful because, yeah, okay, I've used all these things in my life most likely, but to say they're exciting and fun, is that really true? Well, did you know that you can take a turbine and a compressor, hook them together on a common shaft, and now you've got a turbocharger? Well, that's pretty interesting, right? Because cars with turbochargers are a whole lot more fun than cars without, assuming that they work. And did you know also that after the air is compressed, it's actually pretty hot and needs to be cooled down before it goes into the engine so that the engine doesn't destroy itself by compressing that air again? And so there's actually a heat exchanger called an intercooler that takes the hot, compressed, pressurized air and cools it down with more outside air, not by mixing it, but by running it through a heat exchanger so that you can maintain the pressure of that compressed air before you put it into the engine. So that's an example where, yeah, some of these devices do make things a little bit fun. And I think it's probably more fun to take a comfortable shower in the morning than a cold or hot shower. So again, our nods to the mixing chamber. I don't know that I'd call it fun, but I'd call it a comfort device. So now let's apply our steady flow energy balances to some of these pieces of equipment. Let's start with nozzles and diffusers. So we're going to have flow come in from the left and go out to the right. Now the job of a nozzle and diffuser will become fairly apparent after we apply the energy balance to it. Notice it's a single inlet, single exit system. And I'm going to make some arguments about this to explain why we will throw away some of the terms in this equation, because actually a lot of terms in this equation will not be very important. A lot of times nozzles and diffusers, while they may lose heat or gain heat, the amount of heat gained or lost per unit mass is usually really small, because the gases that are even going through this nozzle or diffuser simply don't spend much time there. So each unit mass does not lose or gain very much energy by heat. And so we can cross off the Q dot term. In a similar way, there's no moving parts here, and so the fluid doesn't really do any work, so we can cross off the W dot term. We also will cross off the potential energy change. Yeah, it's possible that the nozzle might be oriented downward like in a, or diffuser may be oriented downward like in a rocket engine, but that height change is just insignificant by comparison to the other changes in flow and thermal energy as well as the kinetic energy. So we get to cross off all these terms. And then if we rearrange the equation to put inlet on one side and exit on the other, where we have inlet on the right, exit on the left, we might note, being a single inlet, single exit system, that we can cross off the mass flow rates on both sides of the equation. In that case, we'd have enthalpy plus kinetic energy leaving equals enthalpy plus kinetic energy entering the nozzle or diffuser. Notice this equation, this energy balance, would apply to either one. Now, at this point, what you should do is go to your book, to chapter 4, and find where your author talks about nozzles and diffusers, and probably highlight this equation, or maybe in the back of the chapter in the summary you might write down this equation for nozzles and diffusers. That way it's really easy to find, because this is our governing equation for nozzles and diffusers. And what it really says is that nozzles and diffusers convert enthalpy to or from kinetic energy. In the case of a nozzle, what it does is it takes in significant enthalpy and converts it to significant kinetic energy, because the exiting stream has to be moving a whole lot faster. It has to have a much higher velocity than the entering stream, and therefore the kinetic energy is much higher. Because notice this velocity of flow, and I'm sorry that it's a capital V, it should be a script V to match what's in the equation. These are velocities in the figure, okay? But the velocity at the exit of the nozzle should be much, much larger than the velocity of the entering gas. And I'll make sure you've got a video from Mythbusters where they pulled a taxi behind a jet engine, and you can see the taxi flip over. I'll give it away. That's what ends up happening, because the velocity of flow coming out the back end of the nozzle of the jet engine is so high that it's just a ridiculously fast velocity, and the wind just catches the taxi and flips it. And that should make some sense to you. I mean, if you're going to push a really heavy jet down the runway and get up to 300, 600 miles an hour, well, you're going to have to have some really large thrust, and so that means you're really going to have to toss the air out the back of that engine pretty hard, which is exactly what jet engines do. So the point is that nozzles and diffusers convert between kinetic and enthalpy forms of energy. In the case of a diffuser, the velocity of flow coming out is much, much smaller than the velocity entering, and therefore you're sacrificing or converting kinetic energy from the inlet to enthalpy in the exit. What about turbines or compressors? Remember, these are reverses of one another. Well, in these we can't cross off the power term, the work term, the W dot term, because that's part of it, right? If you want a turbine to be useful, you include a shaft for output power. If you want a compressor to do anything, you got to put power into it. You got to put shaft power into it. Now, a lot of times these things are insulated, and so there will be no heat interaction. But sometimes, especially in the case of a compressor, you intentionally cool it. So depending on exactly what you got, you may or may not be able to cross off the Q dot term, but you always cannot cross off the W dot or the work interaction term. And so what else could we actually cross off? Well, a lot of times, like I said, we can cross off Q dot, but it depends. But frequently, the kinetic energy change of the entering and exiting stream is small by comparison to the enthalpy change. So a lot of times we'll cross off the kinetic energy change, the V squared over 2 terms, and also, even though the entering and exiting streams may be at different elevations, we'll frequently cross those off, or the potential energy change of the streams off as well. And then what we end up with is that negative of power output in the form of work equals the mass flow rate of the substance, the fluid, typically a gas, flowing through the device, times the enthalpy change from inlet to exit, H2 minus H1. Remember, this is a delta, so it's final minus initial, and 2 is always the exiting state for these. If we apply this equation to the turbine and make it really clear that we're getting power out, well, let's see, power out is positive, so that negative W dot would stay as it is, but if we move the negative sign to the other side, then we'd end up just flipping H1 and H2, and there's our governing equation in the box for a turbine. Again, you'll need to find in your book where your author talks about turbines and compressors, and probably either highlight this equation or write it down, because it's useful when you're dealing with a turbine. On the other hand, with a compressor, the power has to flow in. So power in is negative. There's already a negative sign from the equation, so negative times negative is positive, and we don't have to flip around H2 and H1 on the right-hand side. Okay, so what does a turbine or a compressor do? Well, it trades back and forth between shaft power and fluid power, because really the mass flow rate times the enthalpy represents fluid power. In the case of a turbine, maybe a steam turbine for example, the fluid that comes in has more power than the fluid that leaves, and since that fluid can't be destroyed, it comes out of the turbine in the form of work. In the case of a compressor, the fluid that leaves has more energy, right? It has more thermal energy, it has more flow energy because it's at a higher pressure, and so work must go into the system in order to compress, to do the work of compressing the gas to state 2. So again, this equation W dot N equals M dot delta H is worth writing down next to compressors in your book somewhere, or maybe again in the summary of the chapter 4. So what these things do is convert between work and enthalpy. What about a throttling valve, or a flow restriction essentially? Well, where would you see a throttling valve? Well, you may not know this, but in your air conditioning system, if you have a high pressure refrigerant that has already been cooled a little bit, say it's, you got your air conditioning system running in the summertime, say it's let's say it's 100 degrees outside, and so you've got this refrigerant that you compress the heck out of so it goes up to 120 degrees, you cool it down with outside air, but that just takes it down to 110 degrees. Well, did you know that compression process is what raises the temperature of the fluid, the refrigerant? But if you take that same high pressure and 110 degree fluid and you expand it with a flow restriction, you let it expand, it will drop its temperature significantly, and so now you can generate really cool, cold fluid, about 50 degree Fahrenheit or so fluid, that can be used to cool your home. And it's a refrigerant, of course, so you run it through a heat exchanger. But that's really the heart of an air conditioning system, is a throttling valve. There's many different ways to do it. Some air conditioning or cooling systems for cooling, say, ice in a restaurant, or water at a water fountain, simply use capillary tubes. A capillary tube is just a tube that is real small in diameter, but you force the refrigerant to flow through it anyway. And you can imagine it being a small diameter of flow pipe. It's going to drop the pressure pretty well, right? You can also include things like porous plugs or adjustable valves, or even fixed valves can drop pressure. So let's analyze this and see what really happens. There are no moving parts. Yeah, of course, with an adjustable valve you can pull the gate in and out, or whatever the flow restrictions may be, but most of the time we're talking about a steady state thing, so the valve's just set wherever it is. And so there's no work interaction here, so the W dot term goes away. The fluid typically goes through the valve fast enough, and a lot of times these throttling valves are insulated so that there's no significant heat interaction. So both Q dot and W dot go away. Now, in the case of a fluid, it depends on whether the fluid changes phase, or maybe that fluid condenses, or whatever it may be. The amount of velocity coming out can be different than the velocity coming in, but most of the time that difference is small enough that we still get to neglect the kinetic energy, and as usual, potential energy changes from inlet to exit as a common casualty of this equation. So 9 times out of 10 we're going to cross off the potential energy anyway, right? So what's left? It looks like we've crossed off just about everything in our steady flow, single inlet, single exit energy balance. Well, all that's left is this. And by the way, why bother having the mass flow rate in it? We can simply write that the enthalpy leaving is equal to the enthalpy entering, and this seems like a pretty boring equation, pretty useless. Except it isn't. Let me explain what happens. When you have a throttling valve like this in an air conditioning system, what happens is the compressor compresses the refrigerant in the gas phase. But the heat exchanger takes that gas that's at a high temperature, high pressure, and cools it down enough so that it goes into the liquid phase. It may still be at a relatively high temperature, but it certainly comes out of that heat exchanger as a liquid. That liquid then goes into the throttling valve, and remember, it's a high pressure liquid. As it goes through the throttling valve, and it's an appropriately selected refrigerant and design system, a lot of that liquid, well, some of the liquid will boil off, and it'll go into the gas phase. When that happens, the temperature of both the liquid and the vapor that's leaving in state 2 will be at a relatively low temperature. And so if you think about what's happened from inlet to exit, forget the phase change for just a minute. Because the temperature has gone down, there has certainly been a change in internal energy, right? Not to mention the phase change itself, which represents a change in internal energy, even though it's not a sensible change, it's a latent change, right? So certainly there's been a change in internal energy, but what happened? Well, remember the pressure dropped also, but the specific volume changes. If you have a liquid and it boils off into a gas, that gas is going to take up a heck of a whole lot more space than the liquid did before it boiled off. In that case, we have to remember that enthalpy really consists of two pieces. It consists of internal energy and flow energy. And the pressure times specific volume, that's the flow energy piece, see? So while the temperature may go down and therefore the internal energy or the thermal energy goes from a high level at U1 to a low level at U2, that's compensated for by the flow energy. The flow energy leaving is greater than the flow energy entering. So just because the temperature goes down doesn't mean we've lost energy. In fact, what this says is we've lost zero energy whatsoever. And that may seem counterintuitive because a lot of you feel that temperature represents how much energy something has, and that's not the case. There are other forms of energy. Are dollars in your account the only way of measuring value in a bank account? No, of course not. You can have a safety deposit box with jewelry or gold coins or something, right? Or maybe patented information that's extremely valuable on a thumb drive, right? There's many different ways of storing value in even a bank account. So why wouldn't there be many different ways or many different forms of energy to consider in these devices? So just because the temperature drops doesn't mean that energy somehow just disappeared. No, it simply changed form in the throttling valve. So for incompressible fluids, what typically happens, especially if the incompressible fluid does not boil off, what will happen is the fluid temperature will go up because the flow energy can't change. But what you've done is, well, I'm sorry, let me take that back. What hasn't changed is the specific volume. The pressure drops, and so the flow energy has to go down at the exit. Therefore, the internal energy or the thermal energy goes up. You see this if you ever take your car to a dynamometer, where you put it on the test stand right, and you put it in gear and you give it the gas and just see how much power the engine can generate. Well, what happens is your car is doing work, turning a drum, and that drum is really hooked to usually just a simple oil pump or a hydraulic pump, and all your car is doing is pressurizing oil. Well, what do you do with that pressurized oil? Well, you take it and you run it across a valve where that valve just simply drops the pressure. It dumps the pressure. But that energy, that flow energy, cannot be destroyed, so it goes into thermal energy. And now you've got hot oil that needs to go through a heat exchanger and be cooled to come back and continue the cycle. So in the case of an incompressible fluid that does not boil off, all this does is convert between flow and thermal energy. As a matter of fact, that's all it does in any case, is convert between flow and thermal energy. And so for compressible substances that will change phase, this could be a different story. So depending on the nature of the fluid, the temperature may go up or it may go down, or it may even stay the same. It just depends. You've got to select the right fluid for the particular application. We've only considered single exit, single entrance devices. What about a mixing chamber? Mixing chambers have two entrances at least and a single exit. What could we cross off here? Well, if the fluid comes into the chamber and doesn't move anything, there can't be any work interaction. There's no paddles or anything necessarily. Of course, if there is a paddle in the mixing chamber, in order to increase the effectiveness of the mixing, then you'd have to include that power. But for a simple mixing chamber, we don't have such a device. So the power introduced by work is zero. W dot is zero. And often mixing chambers are insulated, or the fluid doesn't spend enough time in the chamber to gain or lose significant heat. So Q dot will disappear as well. And again, often the potential energy changes of the inlet and exit and the kinetic energy changes are not large enough to be comparable to the enthalpy changes. So a lot of things just go away, and we end up with something that looks quite a lot like what we had for the throttling valve, except in this case we've got potentially multiple entrances and multiple exits perhaps. Most of the time, as I said, it's a single inlet, single exit. So what this says is that all the energy that comes out, or the power that comes out being carried by mass, came in carried by mass. That's all it really says. And the primary form of energy we're interested in here is enthalpy. In the case of the typical mixing chamber where there is only one exit and only two entrances, then these summations go away and we've got one term on the left hand side that represents the single exit and two terms on the right hand side that represent the two entrances and the power that those two ports carry via mass. Now again, we've neglected any kinetic and potential changes, so it's really just enthalpy that we're interested in here. Now if we write a mass balance around this device and realize that it's operating at steady state, the mass flow rate exiting must be the sum of the mass flow rates coming in. That's kind of like saying, you know, if I've got $10 per second leaving my account, and I've got let's say $8 per second coming in from one source and $2 per second leaving, then my account balance is balanced, right? It's not changing with respect to time. It's at steady state. And so that's what we're looking at here. Now if we incorporate the mass balance and the energy balance mathematically in order to eliminate the mass flow rate leaving, then we're left with the equation in the square box. Again, if you understand all of this derivation, that's great. You probably should. But what we really need for a typical mixing chamber is this equation. So all that a mixing chamber really does is mix the enthalpy of incoming streams. It mixes the energy together and puts it back out. How about heat exchangers? Well, if we perform the same analysis, we can argue very similarly to how we did for the mixing chamber, except here the two streams coming in are not mixed, and therefore there are two streams that leave. Now, looking at the system I have, I want you to pause the video after this question. My question, and I'm going to be careful, this is a CISC trap, okay? I'm setting it for you. So this is a heat exchanger. With the system I have chosen, where we've got fluid A coming in that's relatively cold, fluid B coming in the top that's relatively warm, they exchange heat, right, and then move through, is there any heat transfer that I need to include in my energy balance equation? Pause the video and think about it and come up with an answer. Now be careful. Heat is a form of energy observed crossing a system boundary only due to a temperature difference. Is there a temperature difference? Well, sure, the fluids are at different temperatures, but is any heat crossing the system boundary that I define there? The answer to that is no. All of the heat transfer occurs inside of the system, therefore that Q dot in the equation is gone. We don't need it, and that surprises a lot of students. I'll explain it in more detail in the next slide, but for right now, remember, heat and work are only observed crossing system boundaries. Therefore, we can cross off the heat and work terms, and by the way, we're going to cross off the potential and kinetic energy terms as we usually do because they're so small by comparison to the enthalpy terms. So we end up with an equation that is exactly what we had for the mixing chamber. And we'll rearrange it to talk about the power that goes out the exits being carried by mass equals the power coming in being carried by mass. So fluid A and fluid B both carry energy and power into the system, and fluid A and fluid B both carry power out at the lower right side and the left side of the figure. Now if we expand these terms, there are two entrances and there are two exits. So if we consider the exits first on the left hand side, then we've got the 50 degrees Celsius output of A. That's the first term, the mass flow rate of A times the enthalpy at that 50 degree exit. We've also got the mass flow rate of B, which is the heating fluid. It comes at a higher temperature and it exits at 35 degrees Celsius. For inlets for A and B, we have an inlet on the right that comes in with a mass flow rate of A times the enthalpy of that 20 degrees Celsius fluid, and similarly energy comes in, or power is put into the system being carried by mass at fluid stream B, upper left of the figure, and we quantify that rate by the mass flow rate of fluid B times the enthalpy of fluid B that fluid simply carries. If we rearrange this so that we have the mass flow rates in terms of one another, here's what it looks like. And basically all that heat exchangers do is transfer enthalpy from one stream to another. That's all they really do, is move enthalpy around for all practical purposes. Okay. Now, of course, if you have a boiling or condensing process, then of course the density and the specific volume change so much that you may have to take into account some of the other terms, particularly the velocity and therefore kinetic energy term, but that's usually not common. Now, you might have looked at what I just showed you and said, wait a second, this doesn't seem fair. You're just confusing us for fun because it's called a heat exchanger and yet there was no heat transfer in that last equation. Well, let me draw two different systems that are equivalent to that last system. Let me put a system boundary with this white rectangle around fluid A, and imagine that this is simply a double pipe heat exchanger, so the green system is actually revolved around the pipe that fluid A flows through. Okay, in that case you can see that there's heat crossing the system boundary, and I don't get to eliminate the heat transfer term from the equation, but I do still get to eliminate work, kinetic and potential energies, and what I will be left with is this. Now realize that if I'm talking about fluid A, fluid B is not part of that, right? Fluid B does not cross the system boundary for fluid A that I've defined, that white rectangle. Therefore, I only have terms involving fluid A and the enthalpy carried in and out. If I write a similar energy balance for the green rectangle, remember the one that's kind of like a donut, it's a long donut that's been revolved. If I write an equation for that, then the heat transfer rate out of that fluid, Q dot B, is equal to the mass flow rate of fluid B times the enthalpy change between inlet and exit of fluid B. Now notice that if the heat exchanger is insulated well on its outside, all the heat that leaves fluid B has to go into fluid A because energy can't be created or destroyed. So these two are opposites of one another, right? Heat flows into A and out of B, so we need that negative sign. If we then set these two equations together, guess what we come up with? We come up with the exact same equation we had on the last slide, where we used this system, where we just used a combined system of fluids flowing in to, via A and B and flowing out via A and B. So you end up at the same place. It's just a different way of thinking about it. So maybe this will satisfy your curiosity a little bit, and you realize that, yeah, there is heat transfer. It's just in the right-hand figure, it's internal to the system. In the left-hand figure, it's not, and you end up at the same point anyway. Duct and pipe flow also commonly neglect any kinetic and potential energy changes, and so we end up with an equation that relates heat transfer rate into or out of the ductwork, power going in, so a fan or something moving the air around, or a pump pushing something through the duct, and then the enthalpy changes of the flowing fluid. Now there's several different types like this. You've got, I think I mentioned a hair dryer before, for the lower right hand figure. The left hand side, that might be just a simple heating device that has a hot coil where you run air through it and heat up the air for whatever reason without necessarily the fan being included in this. So this could also have heat loss. I know when I bought my house, I don't know why I ever bought this place, I've got it to a better point now, but when I bought it, it seemed like they had broken every rule of construction. They had put the ductwork in the attic. Okay, so they insulated the attic, okay, but the insulation really needed to go because they had put the insulation up against the roof. And that's a really bad idea because then the roof can't really lose heat very well when the sun beats down on it, and so it basically just cooked the shingles. I had to uninsulate the attic, at least under the roof, and leave the insulation in the ceiling. Now my heating system was exposed to the elements, so that's not good. I ended up removing all of that ductwork and putting it between the basement and the first floor and reusing it all. I actually used less ductwork than they used, and I ended up with a better system overall. But anyway, when I looked at this system and I was taking it apart, I was blown away because the ductwork was about 2 foot wide and I think about 8 inches tall. And there was a place where they had joined two sections together, and there was literally about an 1 by 2 foot gap where air was just blowing through this thing, So it couldn't have been efficient at all. It was just a horrible, build quality and design, and I'm glad I changed it. But that might be similar to our heat loss in the lower left-hand figure in the wintertime. You're paying a lot of money to heat this, and I mention that because the rating of the heat resistant strips that were in the ductwork was 15 to 20 kilowatts, something like that. I don't remember right now. I think it was actually 20 kilowatts. But I was probably using a whole lot more than 200 watts because it wasn't just heat loss. I mean, the ductwork was insulated. It was also air coming out, leaking out, being carried by mass. So there were really two losses there. So I had not just one exit for the airstream, I had two exits, and that was obviously a problem.